Question 1. Police use radar to detect speeding cars. A police officer stands at the side of the road and points a radar device at an approaching car. The device emits microwaves which reflect off the car and return to the device. A change in frequency between the emitted and received microwaves is measured at the radar device. The change of frequency is given by, and we have this equation here, where f is the transmitter frequency, v is the speed of the car, and c is the wave speed. The following data are available. Okay? 1. Explain the reason for the frequency change, and we have 3 marks for that. So the first mark will explain the Doppler shift. The Doppler shift is when relative motion between the source and observer causes a frequency shift. And then we want to relate it to this particular situation. So 2, the emitted frequency travels towards an observer that is travelling towards the wave. And then 3, this causes an increased frequency to reflect. That'll do. Sorry about this writing, it's very small there, isn't it? I haven't given myself enough space to write it. 2. Suggest why there's a factor of 2 in the frequency change equation. Well, with the radar we have a double Doppler shift. And we've talked about that in step 1. So in the first shift, we have an approaching car, and the frequency of the original microwave. And then the second Doppler shift is the reflected from the car, reflected from moving car. And the effect that has is waves reflect off moving vehicle, and frequency is further altered or further increased. 3. Determine whether the speed of the car is below the maximum speed allowed. Delta F equals 2FV over C. Let's rearrange for V. Delta FC over 2F equals V. Let's pop in all the data. 9.5 times 10 to the 3 times the speed of the wave, which is an electromagnetic wave, so it's 3 times 10 to the 8 meters per second. 2 times the frequency, which is 40 times 10 to the 9, and that gives us 35.6 meters per second. We're going to take that to 2 significant figures. We can see that the maximum speed allowed is 28 meters per second, so 36 meters per second is greater than 28 meters per second. Car is above maximum speed. Question 2. A train travelling in a straight line emits a sound of constant frequency f. An observer at rest, very close to the path of the train, detects a sound of continuously decreasing frequency. The train is. Okay, let's think of a person standing stationary. If there's a train coming towards it, emitting a constant frequency f, the waves are going to catch up with themselves. So what you would find is an increasing frequency or increased frequency if it's moving towards. So it's not A or B. We know that it's moving away, and the effect of the frequency is the frequency decreases because it's moving away from its waves. The fact that it's continuously decreasing frequency suggests to me that the train is increasing in speed to cause that frequency to decrease even further. So the answer is D. Question 3. Light from a distant galaxy observed on Earth shows a redshift of 0.15. Outline what is meant by redshift. Okay, we want to do the Doppler effect, but we want to do it in the context of electromagnetic radiation and the galaxy. So what we would say is the distant galaxy is moving away from the Earth. This causes the wavelength of the light to increase, and in brackets I'm going to put frequency decreases, and the light shifts to the red end of the spectrum. Question 4. A stationary sound source emits waves of wavelength lambda and speed v. The source now moves away from a stationary observer. What are the wavelength and speed of the sound as measured by the observer? Okay, let's do situation 1. We have, let's just say that's the sound emitter. And that's our observer. Everything's stationary. The wavelength is lambda and the speed is v. Situation 2, this source is now moving away, which means the wavelength of the waves increases according to the observer, but the wave speed always stays the same. The wave speed has got nothing to change in the Doppler effect, it never changes. So let's go to the answers. Start with speed. We know that speed doesn't change, so we can get rid of that and that, so it's got to be A or C. We know that the wavelength will increase in the second situation, so the answer is A. Question 5. The collision of two galaxies is being studied. The wavelength of a particular spectral line from the galaxy, measured from Earth, is 116.04 nanometers. The spectral line when measured from a source on Earth is 115 nanometers. A. Outline one reason for the difference in wavelength. And that's exactly the same answer as we've just mentioned above. The galaxy is moving away from the Earth. The light emitted by the galaxy experiences an increased wavelength, and in brackets I'll put the frequency decreases, which causes the light to shift towards the red end of the electromagnetic spectrum. That's probably more information is needed for 1 mark, but good practice to remember it all. B. Determine the velocity of the galaxy relative to the Earth. We're dealing with electromagnetic waves, which means we want to use the equation for redshift with electromagnetic waves. It's this one. We're not looking at frequency, we can take that out. And we want to find out what velocity is, so let's rearrange the equation. And we have all that data. The change in wavelength is 1.04 nanometers. The actual wavelength is 115 nanometers. And because this is going to be a ratio, we don't need to do times 10 to the minus 9, that's fine. Times 3 times 10 to the 8 meters per second, which gives us a value of 2.71 times 10 to the 6 meters per second. And we'll leave that in 3 significant figures because the least amount of significant figures shown in the data is 3 significant figures. Question 6. 2 lines X and Y in the emission spectrum of hydrogen gas are measured by an observer stationary with respect to the gas sample. And we can see the increasing wavelength is going from left to right. So the red end of the spectrum is here and the blue end of the spectrum is here. The emission spectrum is then measured by an observer moving away. So we know it's going to be redshifted because it's moving away. Which are the correct shifts X star and Y star for the spectral lines X and Y? We know the lines for X star and Y star are going to be on the red end of the spectrum, so they're going to be on the right hand side of the original lines. That rules out A and B, and now we have to decide which one, C or D, is the answer. Let me just take you to the formula for redshift when we're looking at electromagnetic waves. The change in wavelength is equal to wavelength, the original wavelength, times V over C. And assuming that it's moving away at a constant velocity, this is a constant. However, can you see that Y, the original Y, would have a greater wavelength than the original x, meaning the shift in y is going to be a greater value than the shift for x. You can see here that the shift in wavelength here is a smaller value than the shift in wavelength for x. So it's not that one. The answer must be C. Question 8. Outline how the light spectra of distant galaxies are used to confirm hypotheses about the expansion of the universe. So if we're on the Earth here and we see all these distant galaxies moving away from us, we assume that the universe is expanding. So how do the light spectra of these distant galaxies confirm that? Okay, easy. 1. The light spectra from the distant galaxies all show a shift in spectral lines towards the red end of the spectrum. 2. This shift suggests they are all moving away and the universe is expanding.